Welcome to The Explainer. If you've ever stared down an electrochemical diagram and thought, how on earth do all these pieces actually work together without just failing? Well, you're in exactly the right place. Today, we're dissecting the physical mechanics of the galvanic cell. And specifically, we're zooming right in on the unsung hero of the entire system, the salt bridge. My goal for you today is pretty simple. I want to guarantee you don't just memorize this, but that you grasp these core concepts intuitively so you absolutely secure those maximum exam marks when you're asked to explain the whole shebang.
So think about this for a second. Why doesn't a galvanic cell just stop working instantly? I mean, when we think about batteries, right, we picture this smooth, endless flow of electricity. But the reality of chemistry is kind of different. There's this impending doom of charge accumulation that naturally threatens to, well, murder a battery almost immediately after it starts. Without a very specific intervention, absolute chemical gridlock is going to occur within literally seconds.
Okay, so here's how we're going to solve this electrochemical mystery together. We'll start with the anatomy of a salt bridge, move into completing the electrical circuit, and uncover that nasty charge buildup problem. Then, we'll hit the core neutrality mechanism, look at preventing liquid mixing, and finally, wrap up with a perfect score exam tip.
All right, let's dive into Part 1, Anatomy of a Salt Bridge, the physical baseline.
To really understand the mechanics here, we first got to establish our baseline hardware. A salt bridge is essentially a U-shaped glass tube, but it's not hollow and it's not filled with just any random liquid. It is packed with an inert electrolyte that's suspended in this gelatinous medium, very often something called agar-agar. So think of it like a really thick, conductive jelly. And this consistency, it's absolutely crucial. It allows ions to move through it, sure, but it prevents the whole solution from just pouring straight out into the main cell compartments.
Now, what exactly is inside that jelly? Well, we use specific inert electrolytes to make the magic happen. Some of the most common choices are potassium chloride, potassium nitrate, or ammonium nitrate. But the really key word here is inert. We choose these specific electrolytes because they don't interfere with the main oxidation or reduction reactions happening in the cell. No way. They are strictly there to play a supporting role. They're basically the chemical messengers that we're about to see in action.
Moving right along to Part 2, completing the electrical circuit, sustaining the flow. Now, you got to notice this incredible contrast between the two entirely different ways a galvanic cell completes its circuit. On the outside, you've got the external metallic wire. This is basically the superhighway for electrons, flowing rapidly from the anode over to the cathode. But, as we know, an electrical circuit has to be a closed loop, right? Electrons can't just swim through the watery solutions inside the cell to get back to where they started. So the salt bridge steps up to complete that internal circuit. But it doesn't do this with electrons, oh no. It bridges the gap purely through the physical movement of ions. So you have an electron circuit on the outside and an ion circuit on the inside. It's brilliant.
Which brings us to Part 3, the charge buildup problem, a real threat to the system. Let's spatially map this problem out. In the anodic compartment, oxidation is happening. Atoms are losing electrons, sending those negatively charged electrons up the wire. But what gets left behind? You get a massive accumulation of excess positive cations, like zinc 2+, just floating around in the solution. Meanwhile, over in the cathodic compartment, reduction is happening. Positive metal cations are consuming those incoming electrons and plating out as solid metal, which leaves behind an excess of negatively charged anions, like sulfate. So picture this. We have this intensely growing pool of positive charge on one side and negative charge on the exact opposite side.
And this brings us to the ultimate danger, the liquid junction potential. If this massive charge buildup just continues unchecked, the highly positive anode will literally start pulling back those negatively charged electrons, refusing to let them leave. And on the flip side, the highly negative cathode will start repelling any incoming electrons. This aggressively opposes the electron flow. It's basically a massive internal electrical traffic jam, and it will stop the cell dead in its tracks.
Enter Part 4, the core neutrality mechanism, the ultimate hero.
Here is the exact step-by-step mechanism of how our hero functions. The salt bridge senses this dangerous charge buildup and acts as the ultimate equalizer. Step 1. Negatively charged anions from inside the salt bridge migrate down into the anodic compartment. They deliberately flood in to neutralize all that excess positive charge building up from the zinc. Step 2. Positively charged cations from the salt bridge migrate into the cathodic compartment to neutralize the excess negative charge left behind over there. By perfectly balancing these charges in real time, it's amazing, the salt bridge actively prevents the liquid junction potential from ever forming, which allows electrons to just keep flowing freely through that external wire.
Now for Part 5, preventing liquid mixing, the final guardrail.
Aside from its electrical duties, the salt bridge is also a completely critical physical barrier. It prevents the mechanical mixing of those two distinct electrolyte solutions. You might be wondering, why does this matter? Well, because if you just dumped the anodic and cathodic solutions into one big bucket, the chemicals would react directly with one another. They generate a bunch of heat instead of pushing electrons through your external wire. So by keeping them physically separated but electrically connected, the salt bridge completely avoids those direct, wasteful chemical reactions. That maintains and protects the overall efficiency of your cell.
Okay, we've made it to part 6, the perfect score exam tip. Basically, your cheat code.
I really want you to lock this phrase into your memory right now. Nearly equal ionic mobility. Seriously, if you're writing a response about a salt bridge, this is the exact technical phrasing your professors are actively looking for. It's the secret sauce for those maximum marks.
Let's break down exactly what that actually means. When we choose an inert electrolyte, like potassium chloride, it is not just some random choice. The potassium ion and the chloride ion are chosen precisely because they have nearly equal ionic mobility, meaning they physically migrate and travel through that gelatinous agar-agar at the exact same speed. Think about it. If you picked an electrolyte where the positive ion was way faster than the negative ion, they would separate as they traveled. And guess what happens when positive and negative charges separate? Yep, they ironically generate the very liquid junction potential they were designed to prevent. The solution to the problem has to be perfectly balanced, or it literally ruins the entire system.
So I want to leave you with this final provocative thought. Without perfectly mobile ions, could our chemical solution become the very problem that destroys the cell? It really highlights the delicate, beautiful stakes of electrochemical engineering. Everything has to be perfectly balanced, not just chemically, but physically in terms of speed and mobility for this whole system to function. Keep that image of the U-shaped, jelly-filled tube in your mind, constantly balancing the scales of charge. Thank you so much for joining me on this explainer, and I can't wait to dive into our next topic together.